Hi, today we'd like to talk about how you can extend the trig functions to work for any angle, not just angles in a unit circle. And to get us started, I'd like to have you look at my picture here where I have two concentric circles, share the same center, with different radiuses. One is different than the other. I'm going to ask you to think about this for a moment, and I want to drop down an altitude here. And think, that's a right triangle. And if this were the unit circle, that would be a 1. We know that point is xy, so this would be x. I'm going to call it x1 and y1. If you were to go to the larger circle and do the same thing, folks, drop an altitude. So there's a right angle. Now we have the radius, which we don't know how long it is. I'm going to just call it r. The second point up there, though, has an x and a y of its own, so x2 would be that whole distance, and y2 this height. That's starting to look a little cluttered, but I'd love to have you think about this for a moment. I want to draw those two triangles out here. Here's the first one with its x1 and y1 and its radius of 1. Here comes my second triangle. Has its own right angle, and it also contains angle theta. Its own radius, it has its own y and its own x. Now, ladies and gentlemen, these two triangles are not congruent. Okay? One is a different size than the other. However, they do have two angles that are equal to each other. And if you remember your geometry, that means there's an angle-angle similarity going on between those triangles. That means that corresponding sides are in the same ratio. Based on that similarity, we could easily say that y1 relates to y2 the same way that 1 relates to r. And that proportion would be accurate because corresponding sides in similar triangles are in the same ratio. I'd love to have you do this for me for just a minute, though. I want to change where things are located in this proportion, and you'll remember that I can exchange things along the means here and still keep the same value in the proportion, because you'll still have y1 across from r and y2 across from 1. So an equivalent writing of this could be y1 relates to 1 the same way that y2 relates to r. Ladies and gentlemen, that's kind of significant. I want you to think about that for a minute, because that fraction, y1 over 1, that's the sine of angle theta in the small triangle. So the sine of theta right there in the small triangle. And y2 to r, that's also the sine of theta. Folks, these things are equivalent. It doesn't matter how big the radius in the circle is. If we have congruent angles, that is, if they both have the same angle, then their sine ratios are the same. And you could definitely extend that to work with cosine ratios, with tangent ratios. So based on this discussion of similarity for some angle theta in standard position, which has a point P on its terminal side, radius of r, the 6 trig functions can be defined this way. The sine of theta will equal y over r. It does not matter how big the radius is. It's the side opposite divided by the radius. The reciprocal function to sine is cosecant, and the cosecant of theta will be r over y. The cosine, x over r, the secant, r over x, the tangent of theta, it didn't depend on the radius to begin with, and it's still y over x, and the cotangent of theta is x over y. Ladies and gentlemen, these ratios will allow us to find trig functions for any angle in any circle. It doesn't matter how long the radius is. We proved by similarity that the sine in the unit circle will be the same as, or have the same value as, the sine in a circle with radius r. Okay, that is big news in trigonometry. Let's see how we can use that right here. Suppose it says we have an angle theta in standard position. Coordinates -5 and 12 on its terminal side. Okay, I need to see a picture of that, and I hope that you'll get in the habit of drawing this picture as well. -5, 12 is on the terminal side. So here's our angle theta right in there. Now, theta is larger than 90, so we're going to use the reference angle that's formed by the terminal side and the x-axis. That is our angle that we're going to be looking at is right here. Okay, and what we know is -5 is the x coordinate, 12 is the y, and if we're going to do any work with this, we need to know the radius. So we're going to use the Pythagorean theorem, or remember that the Pythagorean triples, 5, 12, 13, okay? So that's come from the Pythagorean theorem. R is 13, and now we have everything we need. We have an x, we have an y, we have an r. We should be able to write all of 6 trig functions for our angle theta based on that right triangle. So the sine of theta is its opposite over its hypotenuse, 12/13. The reciprocal function, 13/12. The cosine of our theta, adjacent over hypotenuse, -5/13. The secant, -13/5. Right? The tangent, opposite over adjacent, so -12/5. And the cotangent, -5/12. All right. Hey, that wasn't too bad. We just had to use the Pythagorean theorem, which we know a lot about, and just remember how the ratios are defined. Suppose we have theta, an angle in standard position, whose terminal side is in Q2. So we're going to be in the same location, general location, that we were just a moment ago. The cosine of theta is -1/2. Well, I remember cosine is x over r. So the x is -1 while the radius is 2, and maybe that looks like this, where here's our angle theta, the cosine, so the reference angle is the acute angle that the terminal side makes with this x-axis. Here's the reference angle, and this is what we're using. The x in that triangle is -1. The radius is 2, and I know this because, whoops, the radius is 2. I know this because I had a cosine, x over r. We got to find the missing leg in the right triangle. So I hope we're going to think Pythagoras, 2 squared equals -1 squared plus y squared. We're going for the y. -1 squared is 1. And when we take 1 away from 4, we get 3. 3 is y squared. Y must be the square root of 3. That's not so bad. So we have x equals -1, y equals square root 3, r equals 2, and we're ready to write those trig functions. The sine takes y over radius, so root 3 over 2. The cosecant is the opposite of the reciprocal of that, so 2 over root 3, but we know that that's going to 2 root 3 over 3. The cosine of our theta is x over r, so -1/2. The secant is the reciprocal of that, -2. The tangent will be y over x, so square root of 3 over -1, or the negative square root of 3. The cotangent, I got to put my theta, the cotangent is going to be the reciprocal of that, so -1 over root 3, but we know that that's -√3 over 3. And there you have it. We can find the trig functions, all 6 of them, for any angle, as long as we remember our right triangle trigonometry. And that, folks, is pretty sweet right there. All right, please go do the U-try, and we'll see you in class tomorrow.